In this video, we'll be looking at the generalizations of the exponential function y equals b to the x, or f of x equals b to the x. These generalizations only work for the case that, again, looks like this. If there's additions up here or additions off to the side, multiplications of any sort, these generalizations don't apply. However, they can help us come to the conclusions of the generalizations for those functions as well. Assuming we've got these ones down, the shifts of this should allow us to define the generalizations of those functions as well. So the first generalization of every exponential function is the domain and the range. The domain for every exponential function is all real numbers. There are no x values that we are not allowed to plug in. Again, the three main functions that have domain issues are radical, rational, and log functions. And those three functions have locations where if we try to plug certain numbers in, we come to incorrect conclusions or values that just simply don't make any sense. For an exponential function, there are none of those rules. Now, however, there is a range problem. If you recall from the last video, there was a issue with the graph hitting negative numbers in the y's. Again, the reason for that is because if I try to plug in negative values to the exponent, the b to the power of a negative number becomes a fraction, not a negative number. So getting back a value that's a negative doesn't really make any sense. So our range is generally going to refer to some value of 0 to infinity, or, again, depending on if this x happens to be a negative, there'd be negative infinity to 0. Again, these are the generalizations assuming that there's nothing added on extra. If I put a plus a here, for instance, if I had y equals b to the x plus a, again, assuming that this x is positive or there's something else in here that could be negative, then the range is going to change so that it correlates to that value of a and not 0 for those two values. The second generalization we're going to look at is the fact that there is no x-intercept. There's no x-intercept. You won't ever find one, again, unless it's been shifted like this. So we can guarantee a point. There is a y-intercept. And for the basic function like this, a y-intercept will always be 0, 1. However, for a function like this or a function like this, and again, we're adding details to this. I'm going to go ahead and put plus h plus k down here. For values that look like this here, the h value will shift where that y-intercept point is going to end up landing, while the k would potentially allow for an x-intercept to exist. Number 3 that's important is that depending on what the b value is, so if b is greater than 1, so if this value here is not a fraction or anything, then we're going to have a graph that looks like this. Okay, if it's a whole number greater than 1, we're going to have a graph that looks like this. Again, it's very much like that of the graph that we sketched in the last video. However, if my b value happens to be a fraction, please make sure that you remember that if b is a fraction, let me go ahead and just assume, for example, that b is equal to 1/3. That means that I have 1/3 to the power of x, which I could rewrite as 3 to the power of -1 to the power of x. Because again, remember, every fraction can be written as a negative exponent just like that. And then that's the same thing as 3 to the negative x. So these two things right here are exactly the same, and a fractional base will force the graph to actually flip around. And that's what that negative in the exponent will do. Again, if there's a negative on the inside of the graph, it flips it in a very specific way, just like a negative on the outside of the graph will flip it vertically, a negative on the inside of the graph will flip it horizontally. So this graph will come down from the negative side and taper off in the positive side, very much like that. Number 5 is b to the x. Y equals b to the x is 1-to-1, and if you don't recall that from previous videos and or notes, that a 1-to-1 function specifically has an inverse. For it to have an inverse, it means that this function does have a perfect function that it correlates into, where the domain and the range swap perfectly for that new function. We'll talk about that particular function later on. Lastly, number 6. As y equals b to the x, as x approaches, in this case, negative infinity, the function approaches an asymptote. Of y equals 0. And so that means that there's a horizontal asymptote. Again, the x-axis in particular is that asymptote. Again, this can shift based on the up, down, left, right shift of the changes in the function. However, for the basic generalization, that is exactly the details of information that are important for us to walk away with for the standard bases before we move on to more complicated examples.